Hello everyone. So in this session we are going to talk about cyclic group. So already we have discussed the definition of cyclic group. So in a cyclic group we can generate the elements by taking the elements from its own group. So that is what we have seen already. So today, in this session we are going to talk about cyclic group in a concept like any cyclic group is an abelian group. So for that reason we have to choose a cyclic group. Let us take G. So G is the cyclic group and it has a binary operator with it. So usually we denote the generator by small a, which creates the elements of that group in a cyclic groups concept. So now in order to prove the concept of abelian, let us assume two elements from G. So what is G? G is the cyclic group. From that cyclic group we are choosing two elements, and since these elements are taken from the cyclic group, they are generators. So let x comma y belongs to G be any two elements, then x can be written as x equal to a power m and y is equal to a power n. We are choosing two elements from the cyclic group where that m and n are some integers. So we call them as integers. That is the power of a, that is the generator a. Since the elements are taken from the cyclic group, we write in the format of generator type. That is why we write a power m and a power n for the elements x and y. Now let us multiply these two elements. That is, we are trying to work out for closure property. So a star, that is x star y, so that is equal to x is nothing but a power m star a power n. So if you add the powers and the base is same, you can write a equal to m plus n, which is equal to a power n plus m. You can rewrite like this. So obviously we can understand x star y is equal to y star x. So it satisfies the commutative property. Since already the cyclic group satisfies all the properties of group, that is closure, associative, inverse and identity. Now in order to prove it is abelian, we are working on the commutative law, and we have understood that it satisfies the commutative property. So we can say that any cyclic group is an abelian group. So the next level, so we are moving into the next level, that is every subgroup of a cyclic group is cyclic. Now we are going to the level of subgroup. So we have a cyclic group, in that we take a subset. So every subgroup of a cyclic group should be a cyclic group. Okay, like how we solved for every subgroup in a group satisfies all the conditions of it, then we call it as a subgroup. Similarly here also we work for cyclic group and we check how it is, that is how the subset of that cyclic group satisfies all the conditions, then that subgroup will be called as a cyclic group. Okay, in order to work on that, in order to give the derivation for that, let us assume capital G as a cyclic group generated by a term A. So A is taken as the generator. As usual, we usually take small a as the generator for a cyclic group. Now from that G is nothing but cyclic group. From that G you take a subset, that is H, capital H. So let capital H be a subgroup of the cyclic group G. So we are going to work on H, because we have to claim that H is also cyclic. Since it is taken from the cyclic group, so it should be cyclic. It should be cyclic in the sense it should satisfy the properties governing the cyclic group. Okay, so that is our ultimate idea here. So in order to say that every cyclic subgroup of a cyclic group is cyclic, let us work on certain things, certain ideas. So we will think on that and we are going to work on that. Okay. So here what I'm trying to say is, if you take an element as generator in a cyclic group, and if you take a subgroup from that is a group which is already cyclic, from there if you take a subset and if you try to generate the elements, you can easily understand it is even cyclic. So it is very clear that every subgroup of a cyclic group should be cyclic. It is a mandatory idea. Okay.